Continuing with the examples and problems related to the data link layer performance, we'd look at some more numerical problems to look at the quantitative behavior. Using this behavior, you would be in a better position to design the simulation scenario. Let's look at the behavior of the data link layer in terms of the addressing modes which are supported in the data link layer, the performance of Aloha as a channel access scheme, and the ability of switch as a device to learn the MAC addresses every time a transmission is made. I've taken these problems from Kuros and Ross, computer networking, a top-down approach. If we want to understand what is the impact of using a certain kind of MAC address on the overall operation and the processing overhead experienced by the receiving network interface cards, and for that matter the switch also, this example is very pertinent. Suppose that we have nodes A, B, and C. They're all connected in the same local area network, and each of these is using a network interface card to do the data link layer processing. Assuming that A has a lot of data to be sent to B, thousands of IP datagrams, and each is encapsulated as a separate frame, if the destination address used by A is that of B, what would be the response of C? Because C is going to overhear the transmissions from A to B because they are on the same broadcast network. Will C's adapter process these frames, or C is just going to discard them? And if at all C processes them, would it pass the IP datagrams to the network layer of its own computer? What if instead of using MAC address of B, A chooses the broadcast address, that is all Fs? How would the behavior of C change? Let's look at the performance of Aloha now. As you know, Aloha literally means no coordination, no time slots. Suppose that we have 4 computers, A, B, C, and D, and they are trying to access the channel using slotted Aloha. So it means from pure Aloha, we move on to slotted Aloha. Now we incorporate the time slots. But still, there's no pre-coordination or agreement between the nodes for transmitting. If we assume that each node has an indefinite number of packets to send, it means it will keep on trying to avail the time slots. In fact, each node is going to try every time slot. If each node attempts to transmit in every slot with probability P, and if the value of P is 1, it means the node is surely going to try in every slot. If the value of P is anything between 0 and 1, for instance 0.5, it will attempt in every slot with a probability of 50%, and it would defer its transmission with a probability of 50%. If you number the slots as slot 1, slot 2, slot 3, and so on, let's try to answer these questions. The first is, what is the probability that node A succeeds for the first time in slot 5? What is the probability that any node succeeds in slot 4? What is the probability that there is success in slot 3? And can you determine a kind of mathematical relationship about the efficiency of this 4-node system incorporating slotted Aloha? Let's see what is the impact of learning MAC addresses at the switch port through this numerical. Consider a network in which there are 6 computers labeled A, B, C, D, E, and F, and they're all connected to a switch in a star configuration. If you assume that B sends frame to E and E replies with a frame to B, for instance, through an acknowledgement frame. Similarly, if A sends a frame to B and B replies with a frame to A, what is going to be the state of the switch table? You can assume that the switching table is initially empty. You need to show the states of the table before and after each of these transmissions and receptions are made. You need to draw it, and for each of these events, identify the links on which the transmitted frames are forwarded and justify your answer.